Hello everyone. In part 8 of free radical also I will discuss reactions of free radicals. And if you watch the previous 2 to 3 videos, it will help you to connect with this video, otherwise it will be difficult to understand. The playlist link for all the videos under free radical you can get in the description box. So here number 6 reaction, because rest of the reactions covered in the last videos. So this is number 6. This is dehalogenation of Ri or RBr. So now we will replace halogen with H. This is the opposite reaction. In the previous reactions we have seen how in case of alkane, carbon-hydrogen bond can be replaced by carbon Br or Cl. But now we are doing the reverse. Substitution of halogen atom by H. Now in this case we are basically breaking carbon-bromine bond. Now look at this value 280 kilojoule per mole. We are also breaking SNH bond. This is 308. And instead we are getting carbon hydrogen bond, and here we will also get SN-Br bond formation as byproduct. That means these two bonds are formed, these two bonds are broken. Now look at the values, the bonds that are formed that are higher bond energy. That means this is a driving force that we can move from left hand side to right hand side. CBr, SNH, these two bonds are broken. CH, SNBr, these two bonds are formed. Now this is the net reaction, but if we look into the mechanism, as we know, when we use AIBN and BU3SNH, it is the initiation, it will be like this. So here we have this AIBN molecule where this radical is generated. Now this carbon radical, it will take proton from that is H dot from SN BU3, and as a result we are getting this BU3 SN dot radical. Now in the propagation step, this radical, it will interact with RBr, and this RBr bond will be broken, and instead we will get SN-Br bond. Now in the second step, this RBr bond, in the second step, this radical, which is carbon radical, it will capture this H from BU3SNH, and as a result finally we are getting carbon hydrogen bond. So we have started from RBr, we are ending with RH. Now this is the general mechanism. We have used R, but if we will see actual example, so this is the example. So here the molecule is very big, but we just have to focus on this part. If you focus on this part, it is just like RBr. And in the right hand side, if you fix this part as R, then see it is nothing but RH. So here CBr bond, that is replaced by CH bond. Okay, so this is number 6 reaction. The next reaction is dehydroxylation of ROH, that is substitution of OH by H. Now this reaction, it is also having a name. You can consider it as name reaction, which is Barton-McCombie deoxygenation. So in this case, first of all, I would like to mention that it is better for 2 degree OH. So sometimes what happens when we have secondary alcohol, just take the examples of carbohydrates, then for reduction for this alcohol, that is from OH to H, this conversion if we want to do, then the traditional method, that is first OH is converted to tosylate, then we are using LAH. This process, this traditional process, there will be some problem. So in that case, for 2 degree OH, if we want to convert to H, then this free radical mechanism, it is better. That is Barton-McCombie deoxygenation reaction is better. Here what we are doing, first this ROH, it is converted to some thiocarbonyl derivative. Now this R group is alkyl group, and the R prime in the right hand side, that may be different types of groups. That is, it may be H, CH3, SCH3, OCH3, etc. Fine. Now when we will see the mechanism, it is not very elaborated. We know because when it is AIBN present, BU3SNH, from BU3SNH we get BU3SN dot. Now this will participate in the propagation reaction. So in propagation, this ROC double bond S R prime is produced. Now how we will produce this thiocarbonyl derivative from ROH, that is not part of this free radical mechanism, so that I have not shown here, and that may vary depending on what type of R prime group we have taken. One particular example we will see in the next slide, but here we have directly written this thiocarbonyl derivative, which is interacting with this BU3SN dot, and we are getting RO, that is we are getting this carbon radical. So here what will happen, this C double bond O, it will take this radical, and one radical will be generated on this carbon. So the radical that will be generated over sulfur, that will interact with SN, so we will get S-SN bond. Next, what will happen from this, now we will go to the next step. Here this R will be removed as R dot. So what is happening here? So this will make that is RO. If it is broken, there will be radical over oxygen, then oxygen carbon, these two will make together C double bond O. Okay, so it is like this. So we are getting R dot, and finally this R dot, it will take proton. Now it will take proton from Bu3SNH, so you can see from the color, and finally we are getting RH. Okay, so this is conversion of ROH to RH. Now we will see the actual example. Fine. So here if you look at this molecule, just fix this portion as if it is R. So it will be now ROH. First we will make this thiocarburyl derivative. So just one method here we are seeing, which is in presence of NaHCH2 MEI, carbon disulfide methyl iodide, this OH is converted to OCS-SME, and now we will see the actual free radical reaction, which is in presence of AIBN Bu3SNH reflux. Non-polar solvent will be there like benzene, toluene, etc. So finally we are getting, just fix this part as R, so it will be RH. So here you can see the first step, we are basically making the thiocarburyl derivative, and finally the free radical mechanism. So this is Barton-McCombie deoxygenation. Another reaction, number 8, now it is decarboxylation. So from RCOOH, now it may be RCOX also, that is you can take RCOCl. There will be substitution of the COH either by hydrogen or X, and this is known as Barton decarboxylation. So what we are doing here? First of all, we have to make this ester, which is Barton ester, starting from RCO2H or RCOCl. Now how we are going to make it? In presence of DCC and DMAP, if we are starting from RCO2H, and here we have this molecule N-hydroxythiopyridone. So this molecule, finally there will be ester formation. So see this oxygen, and now it is linked to this nitrogen. Okay, so this is ester formation. Now this ester we can also make by some other method. See, keeping the basic structure same, that is this part, keeping the basic structure same, we can also take sodium salt, and now we have taken RCOCl. We are also getting the same Barton ester. Another way, again keeping the basic structure same, just focus on this part, basic structure is same but it is little different. Again we have started from RCOH and we are getting Barton ester. So different types of that is different ways are there by which we can make this Barton ester. Once this Barton ester is we have obtained, now until now there is no free radical, right? Once this ester is obtained, next now the actual free radical mechanism will start. Now here if we take this combination, that is Bu3SNH with AIBN, then we will get RH. So this R group, now it will be, that is this part is removed, and now it is taking H from Bu3SNH, finally we will get RH. Another way, and the fate of this part is, now you can see it will be like this. Now it is aromatic ring and there is SN Bu3. So SN bond is formed. Another treatment also we can do. Here also we are getting RH, but see, instead of taking Bu3SNH, now we have taken some thiol type of molecule, PHSH or TBUSH in presence of HNU or heat. Here also we are getting RH. So this part is fixed, that is same as before, but here the byproduct is different. Now we have SS bond. Here we have SSN bond, here we have SS bond. There is a third way. Now we can make RX starting from RCO2H. So in this case we have taken this type of reagent Cl3CX, where X is Cl or Br, again HNU or heat, and So see here, two methods we are getting RH, and the right hand side that method we are getting halogen RX. So it is the net, what is the net reaction? Change of CO2H group either by H or X. Now if we see the mechanism, for mechanism out of these three only one we will choose, and that one is in the combination of AIBN and SN Bu3SNH. So this combination, from this combination we will get this radical. Once we get it, now there will be this oxygen nitrogen bond. This bond is not very strong, so this bond will be broken, and there will be NC double bond formation, and this radical and this radical, these two will connect. That means SN bond will be formed. Once it is formed, now there will be a removal of CO2, that is the actual decarboxylation step, and we are getting R dot. And this R dot, finally it will take proton from this Bu3SNH, and what we are getting? We are getting Rx. Now suppose instead of taking in the final step, if you take some, there is another reagent, suppose you have taken PHSH, then also we will get RH. Suppose instead of taking Bu3SNH, if we take, remember, Cl3CX, then also we can get Rx. So it is not that when you are starting from this combination, the end also you have to do with Bu3SNH, it is not that. So in the final step also we can change the reagent to Cl3CX so that we can get Rx. So all these are general way we have seen the mechanism, because this R group, it may be any group, it may be very large group also. So actual example we need to see. So here you can see the actual example, total 3 steps, 1, 2, 3. So first we have to make the ester. One, the ester is formed. Now the actual radical mechanism, that is for that we have taken PHSH and HNO, and in the final step we have used CCl3Br, because in the final product if you see, it is nothing but replacement of CO2H group with Br. So in the final step we have to use this reagent, that is CCl3X, where X is Br. So we are finally getting, so this is the actual example of Barton decarboxylation reaction. Fine. So that's all for this video. If you find it helpful, please like, share and subscribe. I will meet you in the next video.